Hello students, we have two more mini lessons on probability. This first one is about Venn and tree diagrams, and then we'll talk about binomial distributions. Let's talk about Venn and tree diagrams for a moment. Venn diagrams were named after John Venn, who lived in the 1900s. And they're used to visualize relationships between events in a sample space. Usually we have 2 or 3 events that may or may not overlap. It's more interesting when they overlap. The sample space is usually drawn as a rectangle, and then the actual diagrams are circles. Of course, when we're drawing it by hand, they might look like blobs. Tree diagrams are not named after a human. They're named after the tree, which is found in nature. The tree diagram is used to visualize the multiplication principle of probability. The shortcut prior to this video is whenever you see and, you multiply the probabilities. But this is the actual principle. You multiply the individual probabilities of each event, in this case A and B. And then they're usually drawn with the starting point, just a point, kind of like, all right, I'm going to think about these events happening. And each branch has a probability. You'll see that in practice coming up. Using a Venn diagram is fairly straightforward. Let's work an example together. A and B are events in a sample space S such that the probability of A is 0.6, so 60%. The probability of B is 0.5, so 50%. But the probability of P and B, both events happening, is 0.3, or 30%. So what we need to do is draw a Venn diagram showing the overlapping sets. We'll do that on the right side here, and then we'll just answer a few questions. All right, I have my sample space drawn in black. I have A in blue and B in red. Now I'm going to look at the probabilities, 0.6, 0.5, and 0.3. There's something wrong. The probability of all things must add up to 1. Therefore, that probability of A and B includes some of each of A and B. Therefore, I can't just label A as 0.6 and B as 0.5. I need to start first with the 0.3. There. Now that I know that 0.3 is the probability of A and B together, what the circles A and B share, now I could figure out what A is alone. So if probability of A is 0.6, that means the probability of A alone is 0.3, because that's what's left over in the blue circle. Now for the event B, the probability of B is 0.5, 0.3 is taken up, so I have 0.2 left. Let's take another look. Probability of A is 0.3, the probability of B is 0.2, the probability of A and B together is 0.3. All of that adds up to 0.8, which is 80%. So there is a probability of neither of these events happening, and that's what's left over between 1 and 0.8, which is 0.2. So that 0.2 is any situation, any event that's happening that's not A nor B. Okay, and I'm sure you could think of situations in your life where there are 2 events that could happen simultaneously or separate, or they don't happen at all. Now we could answer the actual questions. Find the probability that A occurs, but B does not. 0.3. Then part C, find the probability that B occurs, but A does not. Well, that's 0.2. And then find the probability that neither A nor B occurs, and we actually did that with our visual, and that's 0.2 as well, which is 20%. And that is how you use a Venn diagram. Using a tree diagram is pretty straightforward as well. The challenge comes with making sure you understand the question. So this one's kind of wordy. Brennan opens a box of a dozen chocolate creams and offers 3 of them to Jesse. So we have 12, 3. Jesse likes vanilla creams the best, but all the chocolates look alike on the outside. So they're chocolates, and some of them are vanilla inside, some of them are chocolate on the inside. If 5 of the 12 creams are vanilla, what's the probability that all of Jesse's picks are vanilla? So some things to consider in finding the probability that all 3 are vanilla. We need to find the probability of picking vanilla on the first draw and on the second draw. In summary, the question says this. We have 12 chocolates. 5 are vanilla cream and 7 are chocolate cream. What's the probability that all 3 picks are vanilla? Let's start with that point I was talking about. So we have this point here, and then Jesse picks a chocolate. Okay, so we have a first draw. So I draw a circle, and I put C for chocolate and V for vanilla. Okay, and she's just picking, and we find out if it's chocolate or vanilla. So this is our first draw. Here comes our second draw. So she's going to draw another chocolate out of the box. If she doesn't like it, she's going to put it back half eaten. All right, so that chocolate, the next pick could also be a chocolate or a vanilla. But then down here, we also have a chocolate or a vanilla for her second pick, right? Okay. Now we care more about this bottom choice here. So let me show you what I'm talking about. Once we create this first draw, we don't really care about extending this tree diagram along this way. We care more about what's the probability of these 3 picks being vanilla. So I'm not going to fill in the top of this tree diagram anymore. I'm just going to use this piece down here. But I do want to fill in the probability. Remember, 12 chocolates, and 7 of them were chocolate on the inside, and 5 of them were vanilla on the inside. Now filling in the second probability for the 2 vanillas, now there are 11 chocolates left because 1 was already chosen, and there are 4 vanillas left because she already chose 1 vanilla. And then that means the chocolate here would be 7 out of 11. Again, we don't care about that top part of the tree anymore. Okay, let's keep going, and this will be the third draw right here. And like I said, I'm not going to do the top, but I'll do this bottom part. It actually helps me sketch the rest of this. Chocolate and vanilla. And then this one is vanilla down here. And this one is chocolate. Okay, I shouldn't even drawn the this part right here because she drew chocolate as the second draw of the chocolate. So I don't really care about this situation here as well. All right, let's fill in some probabilities here. Now this piece, this is 3 out of 10. Chose 2 chocolates already, so 10 are left, and chose 2 vanillas, so 3 are left, and then this one would be 7 over 10. So I'll take those basic probabilities and fill them in over here on the left, where the question is. 5 over 12 for the first draw, 4 over 11 for the second, and 3 over 10 for the third. Now, if we do all 3 are vanilla, then what we have to multiply all 3 things together. 5 over 12 times 4 over 11 times 3 over 10. And we could simplify all of that, the 4 and the 12 and the 5 and the 10 and all that stuff. That becomes 1 over 22. That is the probability that Jesse will pick vanilla, vanilla, vanilla. And that leads right into what we're going to talk about next is a binomial distribution. Binomial meaning we have 2 options. We could either get a vanilla or a chocolate. Now it's time for the second mini lesson on probability called binomial distributions. We'll extend that last example and connect it to the binomial theorem. Woo! Welcome, ladies and gentlemen, to binomial distribution madness. Suppose Tommy, good old Tommy, makes 92% of his free throws. Great job, Tommy. You're doing swell. If he shoots 15 free throws, and if his chance of making each one is independent of the other shots, which is not likely, you get kind of tired, what is the probability that he makes all 15? This is a binomial distribution example because Tommy could either make his free throw or not make his free throw. Let's draw a tree diagram of this binomial madness. I want you to start a little bit to the right of middle on your paper. You should have a big open space. And let's try to be as tidy as possible here. So I'm just going to draw a tree going to 2 possibilities. I have a success and a fail. And if you make a mistake, of course, just erase. Now that is the first free throw. Now let's draw another one and just try to create like a kind of like a triangle here. But don't let your segments be too long. So we have success and fail, and then success and fail. And that is the second free throw right there. And then we're going to do one more. It would be crazy if we did all 15. This diagram would be huge. All right, now what we need to do is we need to make things get a little bit wider here. And so make your triangle actually get wider if possible. So we have a success or a fail. And then for this next one, we have a success or a fail. And so on. So things get a little bit tight, but it's all good. So at the bottom here, what you should have are 1, 2, 3, 4, 5, 6, 7, 8 possibilities, which is 2 to the third power. Now what we'll do is try to fill in some of the probabilities here, and we either have 0.92 or 0.08. 0.92 for all the successes and 0.08 for all of the failures. So we could fill in all the ones in between here, you know, like little things like this guy right here, and this one over here. But we don't really need to fill in every single one because we know what F is and we know what S is. All right, now let's combine some of these ideas. Think about all of the possible outcomes of making or not making the free throws. What we have, we'll do a different color here. What we have are success, success, success. That's a great situation. But on the other side, we have fail, fail, fail. Now think about the other situations. How many are there? Well, we have S, S, F, which is, 2 successes and a fail. But then we also have S, F, F. Interesting, or maybe not quite yet. We have three of these free throws being done. Sorry, so 3 experiments of this event and 2 possibilities for each event. Yes? All right, but then we get 4 possibilities, 4 outcomes. Now, the outcome SSS, the probability of that is 0.92 raised to the third power. All right, that's pretty easy to see just from the picture here, 0.92, 0.92, 0.92. But then this is a little bit, well, I'll do the fail, fail, fail next. Okay, 0.08 raised to the third power. Okay, third power. And that's easy to see as well. We see 0.08 times 0.08 times 0.08. Now let's figure out what the success, success, fail is here. Let's take a look. We could have S, S, F. All right, so that happens once. How many other times do we have 2 successes and a fail? Well, we have S, F, S. That's the same thing. And then we have, over here, we have fail first and then succeed twice. So we have 3 of those. We have 3 of those, which is 0.92 to the second power, because there are 2 successes, and then 0.08 to the 1. There are 1 of these, and there are 1 of these. Now let's follow the success, fail, fail. Where do we see 2 fails? All right, not over here, but if we succeed first and then fail twice, or Tommy does, we have 1 there. And then we have a fail, success, fail, so that's 2 fails. We have fail, fail, success. Oh my goodness, we have 3 of these, which is 0.92 to the 1 and 0.08 to the 2. I hope you start to see this pattern. I hope you could see it already. If not, here it is. I have something raised to the third power, and then I have 2 things raised to a power that add up to 3, and then another 2 add up to 3, and then another 1 that adds up to 3. And then this little sequence, 1, 3, 3, 1, 1, 3, 3, 1, that showed up. How did they show up? Well, we had three experiments, and we're choosing one of them. So this is 3, choose 1. Sorry, 3, choose 0. 0 fails, meaning. And then this is 3, choose 1 fail. And then this is 3, choose 2 fails. Make that clear. 3, choose 2 fails. And then this is 3, choose 3 fails. And it's these numbers, specifically the 1, the 3, and the 1. We didn't really answer the question though, so I'll answer that on the next slide. The probability of 15 successes, it's fairly clear. You just follow that triangle down the far left and you get this 0.92 to the 15. All right, and that would be the probability, 29%-ish. All right, so let's take a look at another specific event with the free throws. Same setup, same probability that he will succeed in his free throw. But in this case, we're wondering what's the probability that good old Tommy will make exactly 10 of his free throws? Well, in this case, what we're going to do is we're going to do 15, choose 10. We're choosing 10, or we're not choosing 5. It doesn't matter. We could either do 15, choose 10, or 15, choose 5. And then what we'll have is 0.92 to the 10, 0.08 to the 5, because that 5 and the 10 must add up to the number of experiments. And whatever that number is the probability that he makes exactly 10. That's equal to 0.00427, or something like 0.4%. Less than a percent. Less than half of a percent. That is all I wanted to share with you. I hope you made some connections in this video and enjoyed probability in general. Thanks a lot for watching.